So I think if the time's right, we got a good group. I'm Dominic, and I'm also joined by Megan Anderson, Kelly, and others in the Primer team. And I'm here to be the MC for Software Demo Days. This is, also, I'm so glad to hear Swara's here. Swara, would you like to jump on and audio and say a few words about the project? Was my muted?
Hey everyone, I'm sorry. I've been having issues with my mic recently.
Oh, not at all.
Well, yeah. But anyway, yeah, Dominic, thank you so much. And everyone, welcome to the third installment of Software Demo Days, where we are effectively showcasing all of the various marine energy software we here at WPTO have been funding through the years, and most of which you can find on Primer's Marine Energy Software Hub. And yeah, through this series, if this happens to be your first one, we simply aim to increase cross collaboration and demonstration of these various software. And we're hoping to encourage just sort of more team building in the broader marine energy software sense. And yeah, so far it's been really great. I think that we've had some really great turnouts, some really great questions. And today particularly is the first day where we're using CoCalc for our demonstration. So hopefully everyone has had their own has downloaded and gotten access to their own CoCalc account and will be able to follow along. And yeah, I'll just throw it back to Dominic. I'm just so excited for the demonstration today.
Much, Swara. So yeah, just as he was saying, this is the first demonstration to be using CoCalc. As we see, this is the third of we got quite a few more. So make sure to tune in to the next couple. And that's kind of all I have. I'm just here to facilitate and help the discussion along, and answer anything in chat, bring the chat questions to the attention of the presenter. But I'm so happy to welcome Hannah Ross, and I can turn it over to her. I'll stop sharing, and she can take it from here and present to us OpenFAST.
All right. Thank you, Dominic. See if I can get my screen shared here. All right. There we go. So yeah, thank you all for being here today to learn about OpenFAST. Kind of a little bit of an overview of what I'll be talking about today, and just kind of a rough breakout of the time. I'm going to first give an overview of OpenFAST, so that'll start with kind of diving into the theory behind the different models that are in OpenFAST. And then, because this is likely to be a bit of a longer demo, we can take a break after the theory portion and before the actual demonstration. And then we'll move into the demonstration, again on CoCalc, hopefully with you all being able to actually follow along and complete the kind of simulations and input file setup steps that I'm doing live. And then a little bit of buffer time for wrap up, any last questions, any specific demonstrations that you want to see. And again, this is kind of flexible timing. And I do want to encourage you to just put questions in the chat, or raise your hand, or come on camera and interrupt anytime you have a question. I kind of prefer that than holding for a specific time. So yeah, please just feel free to let me know or jump in at any time during the overview, or especially during the demonstration. All right, so for the overview, I'm going to talk first about kind of OpenFAST as a whole, and then its specific capabilities, with an emphasis on, of course, marine turbines, and then the structure, so how it's pieced together, and then some details on the theory that's behind each of the different OpenFAST modules that makes up the full code. All right, so I like to show this slide first, just to kind of give an idea of where OpenFAST fits within the full or kind of larger picture of turbine modeling tools. So this is NREL/DOE open source turbine modeling tools. As you probably notice, these are pictures of wind turbines. So a lot of what we're doing, including with OpenFAST, is adapting these wind turbine tools for marine turbines. And so this schematic is just kind of showing that for individual turbines on the top row here, and then for arrays on the bottom row, we have multiple tools that address varying levels of fidelity. So lowest fidelity models used for design exploration for individual turbines are Wisdom and Raft and Floris for arrays, then up to mid fidelity, which we have OpenFAST kind of lumped in this, and then FastFarm and WindFE for the arrays. And then high fidelity, high resolved model, Exawind and SOFA. And then these can also be used for array modeling. So I've circled in purple the models that we have adapted or are currently adapting for marine turbines. So Wisdom and Raft at these lower fidelities can be used for marine turbines, and of course OpenFAST, which I'm focusing on today. And then we don't have an adaptation of Floris for the array model yet for marine turbines, but this is something that we would like to do in the future and provide that kind of array modeling tool. So this is just to kind of orient you. We are looking at this mid-fidelity type of model for individual or single turbines. And that's allowing turbine loads analysis, detailed design, running of IEC load cases, that sort of thing. That's kind of where we're focusing in on today. All right, so the capabilities of OpenFAST. It originated as, like I mentioned, a wind turbine modeling code for land-based wind turbines, and then was expanded to offshore and floating, fixed and floating. And then we have further adapted it now for fixed and floating marine turbines. So the kind of idea behind OpenFAST is that it's an engineering model, so it couples together models to simulate the aerodynamics, hydrodynamics, servodynamics, control, structural dynamics, that sort of thing, in these different modules that I'm going to kind of dive into a little bit further. In its kind of base operation, OpenFAST computes nonlinear dynamics in the time domain, but it can also be linearized. And this nonlinear simulation enables loads analysis for predicting system ultimate and fatigue loads. So again, kind of the application of running lots of load cases for a design, looking at running against the IEC standards, looking at the loads that the turbine is experiencing. And then on the right here is just kind of a cartoon to show some of the different physics that are captured now for marine turbines in OpenFAST. So we have added mass on the blades and the tower or support structure. We have buoyancy now on the rotor. Neither of those pieces were there before for wind turbines. They were present for the structure, the support structure modeling, but we've now added them for the rotor as well. Cavitation on the blades. There's a cavitation check that can warn users if cavitation is detected. We have variation in the wave depth from tidal or storm surges, incoming waves, and then we can also model turbulent currents and tides incoming and their impact on the both the support structure and the rotor. And like I mentioned, OpenFAST can also be linearized about a given operating point. And so this enables further analysis, modal analysis, controls design and instability studies, that sort of thing. So it can kind of output the equations needed to generate or use a linear model. And then the basic structure of kind of OpenFAST itself is really what we refer to OpenFAST as kind of the glue code, and it couples together these independent modules that model specific dynamics. So there's a module that models the rotor, aero, or hydrodynamics, a separate one for the structural hydrodynamics, a separate one for the structural dynamics of the rotor and tower, etc. And this OpenFAST glue code couples together each of those modules and kind of passes the needed information from one module to the other. And when the original FAST was rewritten as OpenFAST, this kind of modularization was emphasized to enable data encapsulation for specific physics and components. And that enables more code flexibility in that certain modules can be run by themselves. So you can run just aerodyne if you want to model only the rotor, aero, or hydrodynamics, for example, and that enables these modules to also be more easily coupled or called from different external codes. So different driver codes or even some commercial codes can call pieces of OpenFAST and run with that if needed. That also enables us to run more than one instance of a module simultaneously, which is being used for a couple of applications that I'll talk about in a few minutes. So like I said, some work over the past few years has really emphasized adapting OpenFAST for marine turbines from wind turbines. And the features, the capabilities that we identified as really needed to more accurately model marine turbines are listed here. So as I mentioned, buoyancy on the rotor, nacelle, and tower, again, not considered for wind turbines, but something that we need to put in there for marine. The calculation of inflow accelerations. So the way that the inflow was set up was separate inflow seen by the turbine and then by the support structure, as you can imagine, makes sense for a wind turbine. But for a marine turbine, the whole structure is experiencing the same inflow subject to waves and currents. And so we needed to be able to calculate the inflow accelerations from turbulent currents in order to account for fluid inertial loads. So that's something that was added. This was done again for the waves, but not for the currents. And so now we can capture those fluid loads from turbulent currents in the accelerations on the rotor and the support structure. Wave and current velocity superposition. So again, this was done before just for the inflow that the support structure was seeing, but now the rotor is also being subject to wave loading and wave velocities. So we've added the ability for the waves and the currents to kind of come in as a consistent inflow and those velocities to be superimposed. And that's what the inflow that the entire structure sees. So it sees this consistent inflow affected by the waves and the current. And then, as I mentioned, added mass loads due to body accelerations within the fluid, and then these inertial loads due to flow accelerations. And then also the cavitation check, which was one of the first capabilities added for marine turbines, which just lets the user know if the code thinks cavitation is occurring on any of the blades and at which kind of location along the blade it detects cavitation. All right, so WPTO has been supporting a lot of this OpenFAST development, and we have an ongoing project called Aquarius that is adding more features for marine turbines, and those I've listed out here. So these are some additional features that were identified as important but weren't able to be included kind of in the original scope of these modifications for OpenFAST. And the first is lifting loads on faired towers. So a lot of marine turbine designs do have kind of the tower or the support structure connecting to the rotor with a faired design to minimize flow disturbance and impact on the power performance. And we want to try and capture any lifting loads that might come from this airfoil shape of the tower. So right now, as the tower is defined in Aerodyne, the typical way it's done, it just assumes that it's a cylindrical shape, again, which is most common for wind turbines. And so we're adapting that to have some more flexibility to capture these different shapes that marine turbines come in and the associated loads with that. We're also adding a dependence on the KC number in the loads on the support structure. And I'll talk a little bit more about that in when I address the Hydrodyne module. But this is just to try and increase the accuracy somewhat for the coefficients that are used in calculating the hydrodynamic support structure loads. We're adding in a new dynamic stall model as well that was published recently, and it's shown to be promising for turbines that experience dynamic stall, particularly cross-flow turbines, and with the ability, the added flexibility of the rotor module in OpenFAST to model more non-traditional geometries like cross-flow turbines, pitching and heaving airfoils. We think it's important to have this dynamic stall model as an option and potentially improve the accuracy for those specific operating conditions. And then I mentioned that we currently have wave current superposition as a way to capture the impacts of the waves and the currents on the velocities that the system is seeing. But what we really want to do is better model the actual coupling between the waves and currents and the effect that the current has on the wave frequencies. And so that's something that's planned under this Aquarius project as well. So having that better, more realistic mathematical representation of the interactions between the waves and currents rather than just simple superposition. And then finally, important for marine turbines is flow confinement. So we often see effects of the presence of the seabed or the surface, the free surface, if a floating turbine is close to the free surface or deployed in arrays where the flow confinement becomes significant and affects the flow through the turbine and its performance. And that's something that we are planning to include in OpenFAST within this Aquarius project as well. All right, so the existing OpenFAST structure, these images give just kind of a visual overview of what I've been describing, with OpenFAST acting as the glue code that couples together all of these different sort of independent modules. And this is a list of the primary modules that are included in OpenFAST currently. So we have Elastodyne, which models the structural dynamics. Beamdyne is an optional module that can be used in place of the Elastodyne representation for the blades specifically. Aerodyne for the rotor fluid dynamics. Inflow wind models the wind or current. Servodyne, the control and electrical drive dynamics. So enables different control schemes to be implemented into the model. Hydrodyne on the substructure hydrodynamics, and then Subdyne for the substructure structural dynamics. And then there's a few different options for a mooring representation, including an interface with the commercial code Orcaflex, and then a couple of modules that model ice as well. And then this is a new module, C-state, which I sort of added in here in a non-eloquent way. And this was just added in, I think, the newest OpenFAST release 4.0. And previously, the wave representations were generated within Hydrodyne, as well as the analysis of the hydrodynamics. And now this is split out to kind of mimic how inflow wind and aerodyne works, such that the wind and the currents is generated in inflow wind, and then the waves in C-state, and then those are passed to the hydrodynamic modules, so aerodyne and hydrodyne for the rotor and the support structure hydrodynamic calculations. C-state does have the ability to model very simple currents, which I'll talk about a little bit more. But for the purposes of marine turbines, we often want to get those currents from inflow wind instead of the simple currents generated in C-state. And then a graphic of the modules and data passing is here on the right. So for a marine turbine, this is kind of showing how, specifically for a floating turbine, how the modules, how simulation might be set up and information would flow from different modules to each other. So the moorings interacting with the substructure dynamics in subdyne, interacting with the tower, nacelle, rotor dynamics in elastodyne, and then this nacelle dynamics interacting with the control system, the power generation, and then that flowing through to the drivetrain and rotor dynamics. And then, of course, these structural loads being passed back and forth with the modules calculating the fluid loads. So aerodyne for the rotor, hydrodyne for the substructure. And then for marine turbines, the way we have the inflow information set up is both aerodyne and hydrodyne query the C-state module to get information about the waves. And then C-state queries inflow wind to get the current information, adds that together, and then passes that full velocity information back to aerodyne and hydrodyne. So again, a bit different than how it works for wind turbines, but we're modeling different conditions. So this is the setup that we have for marine turbines. And then again, under another project funded by WPTO, we are developing the capability to support multi-rotor modeling. And I give credit to Jason Yonkman here for the creation of this image, and apologies that I don't have it for a marine turbine, but kind of the same idea here applies. So this will enable multi-rotor modeling, and the implementation is generic, so it can work for fixed or floating wind or marine turbines again. And this is really important for marine turbines because, as I'm sure all of you know, the locations where they are deployed can often be depth constrained. And so a lot of marine turbine designs are dual rotor to increase just the power capture area. And so we are generalizing OpenFAST to be able to model multi-rotor turbines up to N number of rotors for a single support structure. And this is an overview of what the module pathing and connection might look like for a two-rotor turbine. In this case, it's a two-rotor floating wind turbine, but again, pretty similar kind of connections for a multi-rotor in-rotor marine turbine. So in this case, we have one support structure, which is represented by a single instance of moordyne and subdyne, and then multiple rotors and towers. So that's one instance of elastodyne and servodyne per rotor. And then those instances talking to aerodyne and hydrodyne. So again, one single support structure, talking to one instance of hydrodyne, and then multiple instances of elastodyne and servodyne. The reason that there's only one instance of aerodyne here is because a separate piece of work a couple of years ago actually generalized aerodyne to handle multiple rotors already. So one instance of aerodyne can model multiple rotors. And so these multiple elastodyne and servodyne instances just talk to one instance of aerodyne, and then a similar kind of pulling of that inflow information from inflow wind and sea state. This work also includes the implementation of a supercontroller to allow kind of talking between the controllers of each of the rotors on the support structure. So that's kind of what it looks like for multiple rotors and where we're headed with that piece of development. So now I want to dive a little bit more deeply into each of the modules, what they model, the dynamics that they represent, and some of the theory that is underlying each of them. Yeah, Swar, did you have a question?
Sorry, that was an accidental raising my hand. Please keep going on.
No worries. Yeah, so I think it's helpful to kind of get an understanding of the assumptions that underlie these models and kind of what we're actually doing when we piece together each of these different submodels to model these different dynamics. And so this is showing each of the primary modules that I mentioned, kind of pointing to the specific parts of a marine turbine. So again, hydrodyne and subdyne on the support structure, elastodyne for the tower and nacelle, the tower and rotor nacelle assembly, servodyne for the controls, beamdyne can model the blade structural dynamics, aerodyne for the rotor hydro or aerodynamics, inflow wind and sea state for the inflow conditions, and then a few different options for the mooring model. So kind of a high-level overview of each of these. Again, hydrodyne uses two different representations, a strip theory approach and a potential flow approach for the support structure hydrodynamics. Subdyne is a linear FEA, finite element representation with a modal reduction for the support structure dynamics. Elastodyne has two representations, linear modal and multi-body for the tower and blade structure. Servodyne, again, controls and drivetrain dynamics. Beamdyne, geometrically exact beam theory as an option to replace the linear modal representation that's in elastodyne for the blades. A blade element momentum and free vortex wake option for aerodyne. Then wind or current inflow and inflow wind, waves and sea state, and then moordyne, which is the mooring model that I'm going to focus on in this presentation, the uses lumped mass discretization and strip theory. All right, so I'll go into a little bit of depth for each of these modules just to kind of explain what their capabilities and some limitations are, and then just a little bit of the theory behind each of them. So for elastodyne, this structural module is limited to axial flow turbines and to 2 or 3 bladed rotors, but it can model upstream or downstream turbines, and again, both fixed and floating for wind and marine. And for the marine turbines, this took a little bit of a reimagination of kind of the coordinate system and how Elastodyne was able to define where kind of the origins of the turbine were placed. But for a fixed marine turbine, the assumption is still that the global origin is at the mean sea level, which is the same definition used for wind turbine modeling. So that's consistent across the entirety of OpenFAST. But now the definitions of the turbine locations are just negative in the z direction. And then that's the same for the floating case. But here we've allowed the rotor and nacelle to be defined below the support structure and tower. And so so Elastodyne, what's represented in here again is the rotor nacelle assembly, the tower, and then attached to a platform, which is just a single point that experiences rigid body motion. There's two structural representations in Elastodyne, like I mentioned. So one is a multi-body, which is used to model the platform, the nacelle, the hub, and the generator. So kind of all the masses and inertias associated with those pieces. The platform rotations assume a small angle approximation, but the other multi-body degrees of freedom, the nacelle, hub, and generator, can exhibit large motions. And then there's a separate representation for the blades and tower. This is a linear modal representation, again, a small angle approximation. And here, these dynamics depend on user-specified mode shapes. So the user has to actually go in and input what the mode shapes and frequencies look like for the blades and the tower. It assumes straight and isotropic beams and looks only at bending degrees of freedom and not twist. And then for each module, I have on the right here just a kind of flow of the inputs and outputs. And so for Elastodyne, it's taking in those aero and hydrodynamic loads, controller commands from servodyne, substructure reactions at the transition piece between Elastodyne and subdyne if it's used, and then outputting this structural information. So the displacements, velocities, accelerations, reaction loads. So how the device is structurally reacting to those fluid and other loads and inputs. And then Beamdyne is the module that can, again, replace the Elastodyne structural representation of the blades. And Beamdyne is based on nonlinear geometrically exact beam theory. And so it allows for much larger deflections and was designed to kind of account for the increase in large flexible blades that was seen in the wind energy industry and enable those large displacements of the blades to be modeled more correctly. So for Beamdyne, it takes in full 6x6 cross-sectional mass and stiffness matrices for the beam properties. It has stiffness proportional damping, and it also uses a curved and swept reference axis. So the blades can be defined as being initially curved and swept, and then deflect even further from there. So just similar to Elastodyne, takes in those rotor, aero, or hydrodynamic loads and the root motion, since it's just modeling the blades. That's kind of the reference point. And then outputs the blade motion and root reaction loads. And then Aerodyne, which again is the rotor, aero, and hydrodynamic model, has two options for solving the rotor behavior, blade element momentum, and free vortex wake. And these can be used one or the other. And then it also includes a couple different models for the airfoil dynamics, a quasi-steady model where the user-defined lift and drag coefficients are just kind of used directly, and then an unsteady model which employs empirical dynamic stall models to add corrections on top of those lift and drag coefficients to try and account for the effects of dynamic stall. But both of these models rely on user-specified polars. So these are inputs that have to be provided by the user, the lift and drag of the airfoils that make up the turbine blade. And then Aerodyne also includes some representations of the interaction between the tower and the rotor, as well as the effects of tower drag. So the drag on the tower, and then the tower dam and shadow models to try and capture what the effect would be on the rotor of the presence of the tower and the inflow that the rotor is seeing. So for Aerodyne, we have the turbine displacements and velocities and the wind velocities, and then it calculates how those translate into the aerodynamic load that the rotor is seeing. And then a little bit of detail just on each of the specific theories in Aerodyne. The blade element momentum is an industry standard implementation, so combination of momentum theory and blade element theory, which solves for the induction factors that are used to calculate the power and thrust coefficients. And then the free vortex wake model that was implemented, which is called OLAF within Aerodyne, takes a different approach to the rotor hydrodynamics. So it's a Lagrangian approach, and the wake is discretized into markers connected by vortex filaments. So in the near wake, it's a hybrid lattice, and then a filament for the tip and root vortices. This is a kind of higher fidelity than the blade element momentum approach. It's also more computationally intensive, but it is more flexible. And so within Aerodyne, there is now the capability, I mentioned, to model multiple rotors already. And so when Aerodyne is run by itself, it can model with OLAF any sort of arbitrary collection of lifting bodies. And so this vortex representation enables those hydrodynamics to be captured, and the interactions of the vortices and the wake produced by the various lifting bodies to interact. So it enables more kind of flexible modeling and will be advantageous to be used for the multi-rotor representation when we want to see what the effect of one rotor on the hydrodynamics of another is. And then the inflow wind module, this provides information about the inflow velocities and accelerations. And this can be, again, for winds or for current. And there are a range of ways that we can define the inflow in this module. So it can just be a steady, non-sheared inflow. It can be uniform across space, but time varying. It can have full field turbulence representations provided by several different sources. So the TurbSim turbulence generator, or from the wind turbine modeling codes bladed in HAWK2, or we can have user-defined full field inflow inputs. So for inflow wind, this inflow information is pre-computed And then different positions are queried by the modules that need them. And then the flow information at those specific points is passed to the modules that are asking for that. And then C-state, which is kind of the analog of inflow wind for the wave definitions, pre-computes wave velocities and acceleration. So it can do regular, irregular, or white noise waves using these different spectrum definitions. It defines wave direction and includes directional spreading. And like I mentioned, it can also define these three kind of simple current profiles within C-state. But for marine turbines, we often, or we want to use the inflow wind definition of current so that the full system is seeing a consistent inflow, and we can represent turbulence if we want to. All right, the Hydrodyne module models the hydrodynamics of supporting structures, and there's a couple of different models available. So there's a strip theory representation, which uses the Morrison equation. This is typically to be used just for slender members, which have a relatively small diameter compared to the wave. And it can calculate inertia, added mass, viscous, and buoyancy loads on the structure, and represents multiple interconnected members. You can see on the left side picture is an image showing strip theory nodes for this semi-submersible platform here. There's also a potential flow representation, which uses inputs from WAMET or some other boundary element code. And it's typically used for larger platforms so that have pieces or elements that have larger diameters, and models the radiation, diffraction, and buoyancy loads. And you can also do a hybrid combination of these two models. So for Hydrodyne, it takes in the substructure, displacement, velocity, acceleration, so just that structural information, and then outputs the hydrodynamic loads from the fluid forcing. All right, the Servodyne module, again, controls the, or enables the control and electrical drive functions. So it has several different actuators that can be used. Blade pitch, generator torque, high-speed shaft brake, nacelle yaw, and then structural controls. Was there a question?
Hey, Hannah. Yeah, I actually just had a quick question on the last slide. When you said that a hybrid approach could be used, I'm assuming that means that like someone could pick and choose which method they use for the different bodies. Is that correct? So maybe for the smaller, slender members, they could use strip theory, and then for the larger components, they can use WAMET. Is that how they use the hybrid approach?
Yeah, and you can also get, I think, some loads from one part of the model and some loads from another part of the model as well.
Okay.
Or from one of the models.
Yeah,
and some loads from the other model.
Okay, I was just curious how that works.
Yeah. Yeah, so for Servodyne, there are a few kind of built-in implementations that can just be automatically turned on for kind of simple controls. But it's really designed to be used with a user-created controller, so it can plug into a DLL that a user brings to kind of input any proprietary controls or anything that they might want to test out with their model. And then a couple of different interfaces with MATLAB and Simulink and LabVIEW are available. So then for Servodyne, taking in these structural motions, loads, and wind measurements, and then outputting the controller commands and reactions. And then for Subdyne, again, this is the substructure structural dynamics model, and it uses a linear frame finite element beam representation, and then does a kind of modal reduction or dynamic system reduction of that for the simulation. And so this is showing the finite element discretization of a tripod platform here. And then this interface node is the connection point between the structural representation in Subdyne and then in Elastodyne. And so for Subdyne, it's taking the hydrodynamic loads and then the displacement velocities and accelerations at this transition piece. Again, that's the interface with Elastodyne, so that's kind of the reference point for the Subdyne calculations, and then outputting the substructure displacement velocities, accelerations, and reaction loads. And this is showing kind of a flowchart of how the calculations are done in Subdyne. So having that finite element representation that's then reduced for the simulation. And then the actual model used during the time stepping is the state space model. Yeah. Is that Rob?
Yeah, thanks. Question about either this one or if it's somewhere else, but is there anywhere where like let's say friction with the seabed would be modeled for a platform like this?
Sorry, you're cutting out just a little bit. Did you say the seabed?
Yeah, like interactions with the seabed, so like substrate friction for like a gravity platform or sliding or overturning.
Yeah, there is a soil dyne module, which isn't used super frequently, and I haven't included here, but that does model more of the interaction of the support structure with the seabed. All right, and then the last module that I'll give an overview of here is Mooredyne. So this is for the mooring dynamics, and it is a lumped mass representation. So this schematic here kind of shows that it's an array of these spring mass damper representations strung together, and it can model taut or catenary lines and include kind of all of these, capture all of these mooring physics here. Elastic stretching and damping, still water, added mass and drag, the apparent weight, et cetera, as well as seabed friction with the mooring lines. So it's dependent on the platform displacement, and then gives the line tensions and line displacement as output. All right, so that's kind of it for a quick run through of all the different module theories. And I think, yeah, thanks, Jason. Jason has added a extra explanation in here about the soil structure interaction. So yeah, feel free if you have any more theory questions or questions about the module to raise your hand or put it in the chat. Otherwise, I'll go on to talk about a little bit of the kind of what the outputs look like and some additional ways that OpenFAST can be used before we take a break and then jump into the demo. So this is an animation created using the visualization output capabilities of OpenFAST. And this is showing a floating marine turbine. So this is the turbine that we're going to analyze in the demonstration. And then just to kind of orient you a little bit, this is a well, the turbine itself is actually the RM1. So the reference model that was developed in about 10 years ago via the DOE reference model project. So this is the RM1, which was originally a two-rotor fixed bottom turbine. And we've just taken the definition of a single rotor and mounted it on this kind of simple adapted semi-submersible platform. And this was just to create kind of a stable example case that we could run and use in our code development and use kind of as a demonstration. Certainly not trying to make an optimized platform or anything like that. But this is showing a simulation of this floating platform using, again, sea state for the waves, hydrodyne, and subdyne representing the platform, aerodyne, elastodyne for the turbine. And you can see kind of the initial surge offset at the beginning of the simulation, and then kind of the platform motion as it reacts to the incoming waves and current. And then as well as the kind of the mooring line displacement too.
At what point do you thought the turbines should have their own turbine? But yeah, what he said about.
All right, some resources for yeah, sorry, Swara, did you have a question?
Yeah, Hannah, thank you so much. If you could go back one slide, please.
Yeah.
I'm curious about however much you can answer this. I mean, this is so brilliant to see, but specifically the level of precision on the waves themselves in the simulation. Can you possibly explain more about that, just out of curiosity?
The level of precision of the waves as far as like how they're modeled according to
how they're
like
modeled and how they're portrayed in the simulation itself.
So for I guess the regular or the different representations that the state can input, regular and irregular waves according to these different spectra that you can choose. And so you specify like the wave height, time period, that sort of thing to define the flow field or the wave field. And so those are just kind of represented mathematically according to those parameters that the user inputs, and then the wave spectrum that's chosen. And then the C-state and hydrodyne does track and represent. And I think this is a somewhat recent improvement in hydrodyne, but the ability to track and represent the changing kind of exact free surface effect on the hydrodynamics for these surface piercing bodies. And I think that's more exactly represented for some specific features or physics than for others, as far as the representation at the free surface and its interaction with the body. And then were you asking kind of about that or about like the visualization here?
Honestly, both. You've already explained like quite a lot already, but yeah, I just really appreciate the answer. Thank you.
Yeah, sure. All right. So for the OpenFAST resources, these are OpenFAST is hosted on GitHub, so all the source code is there, and the documentation is linked from there as well. So probably the two kind of main pieces are this documentation, which is on Read the Docs, and again, linked from the GitHub repository, and it has information on installing, testing, user documentation, which details, again, the theory and kind of inputs and outputs for each of the different modules. There's also developer documentation for people that want to do code modifications, etc. And then the code itself, again, hosted on GitHub. This higher level repository has a few different code bases. So the OpenFAST source code base itself, as well as a repository of tests that are used for regression testing, but are often a good place to start for example cases, and some pre and post-processing tools as well. For questions, there's the NREL forum. This is where we really encourage folks to post questions as well as look for similar questions that may have been asked before. And then the GitHub issues page for reporting kind of issues or bugs with the code. And both of these are actively monitored by the development team and do our best to respond quickly to questions and address issues as we can. So there's a couple of kind of additional uses or capabilities of OpenFAST that I do want to mention. So the first is the OpenFAST coupling with the Sandia code OWNs. So like OpenFAST, OWNs was originally developed for wind turbines, but has a more generalized representation for the structural dynamics. And so we have now a coupling between OpenFAST and OWNs that allows cross-flow turbine simulation in OWNs with the full kind of structural dynamics included. So because Elastodyne is limited to 2- and 3-bladed axial flow turbines, this coupling allows us to take advantage of a lot of the features and improvements that we've made to OpenFAST for marine turbines, but apply them to the simulation of cross-flow turbines as well. And so this, furthering this development and this coupling is something that we're doing under the Aquarius project as well. We also use OpenFAST within a kind of larger control co-design optimization framework called CTOpt. So this was developed under a recent ARPA-E project and is designed to pull together some of these different models at different fidelity levels that we have at NREL. And OpenFAST here is the highest fidelity level used within CTOpt, but this is kind of a wrapper or framework that enables design iteration among these different model components, and then enables integrated control co-design at the same time. And so this has been developed over the past few years and is kind of wrapping up, and we're working on making everything publicly available and well documented for the CTOpt project. And this is, again, will kind of pull in the all the capabilities and features that we have available in OpenFAST for marine turbines. All right, we are right at 12 o'clock, very surprisingly. And I have a few slides just to kind of introduce the demonstration. But I think we can pause here and if there's any questions, address those. Otherwise, I was thinking we could take about a 10-minute break before the demonstration and then come back and jump into the co-calc piece. All right. It's 11 past, so I will get started again. So for the second part, we're going to be looking at running OpenFAST for some different marine turbine cases. And the primary case that we're going to be looking at is this same turbine geometry from the simulation output that I showed previously. So again, this is the 500 kilowatt RM1 turbine designed in around 2011. It's two-bladed, variable speed, variable pitch, 20-meter rotor diameter, and a 1.9 meter per second rated speed. So we took these specifications from the reference model project and reports and built an OpenFAST model of this, including the blade, structural and aerodynamic properties, the nacelle and hub, drivetrain specifications, and the operating profile. And then again, because this was or is a fixed bottom turbine, we have a fixed case that is just this turbine with a single rotor, with the tower assumed to be driven to the seabed. But then for the floating case, we designed this stable quad style semi-submersible platform that the turbine is attached to. And so there was a bit of kind of iterating that we had to do to make sure that the platform and the turbine would work together and produce a stable simulation. And again, just to emphasize, this is supposed to be a robust platform that won't present issues for the simulation and will be, relatively stable and relatively easy to model as we're introducing these new features into OpenFAST and giving us the ability to test them on this kind of fairly well-behaving system. So the platform has large diameter columns, heave plates on the bottom, and a catenary mooring system. We also do have a faired tower in here, which we're adding the ability to be able to model. So kind of designing the test case for the capabilities that we are adding. And then just some information here about the platform structure. And this case is, all the input files for this case are on OpenFAST in that RTest repository that I mentioned within the MHK RM1 floating folder. So for the demonstration, again, these are kind of the primary OpenFAST modules, and the cases that we're going to be looking at use the Elastodyne, Aerodyne, Influend, C-State, Hydrodyne, and Mooredyne modules. So we are not looking at a case that involves Beamdyne, Servodyne, Subdyne, the other mooring models, or any of the ICE dynamics. And these are the modules that are used for the RTest case. And as we add more capabilities, we are building these out. So I hope to have an example case for a marine turbine that uses Beamdyne, Subdyne, et cetera in the future. But for now, these are kind of the modules that we're going to look at within the example cases. And then for the first simulation, at least, we're going to look at steady 1.9 meter per second current, which is the kind of rated operating condition for the RM1 with power loss shear for the inflow, no control. So we don't have servodyne connected. We just have a fixed rotational speed specified. And then we have the only the platform degrees of freedom turned on in this simulation. The actual example cases on the repository have more degrees of freedom, so that just means allowing flexibility in the blades and the tower instead of assuming that they are rigid. But for the purposes of the demonstration here, we're running on CoCalc, which has kind of limited computational power, so trying to kind of simplify the simulation as much as possible and let it run as quickly as we can. So turning off some of those degrees of freedom and that flexibility in everything except the platform motion. And then we'll look at this in a lot more detail when we look at the actual input files, but just to give you kind of a heads up, as to what these look like. This is an example of one OpenFAST input file, and they have a similar layout where they use kind of this three column approach of the value defined on the left. This can be a numerical, a logical, a flag, or a string, kind of depending on the specific parameter. And then the keyword telling you what the variable name is, its identifier, and then a description of that variable. So they're all text-based input files that follow this kind of same format. And we will go into CoCalc and open up the input files for this floating marine turbine test case. Take a look through some of them, and then start trying to run some of the simulations. So at this point, I think I will stop sharing, and then Megan, if you want to take over for a minute and get everyone oriented to CoCalc.
Sweet. Yeah, sounds good. Thanks, Hannah. All right, let me share my screen now. Okay. Can everyone see this? Yep. Okay. Sweet. So this is CoCalc, as Hannah was saying. Not only for OpenFAST, this is where all of your software demo days projects that will use CoCalc will live. Here's a quick video showing you kind of what it is. It's an online collaborative software tool. So when you get onto CoCalc, you're signed in, you'll see something like this. And then the Your Projects tab on the top left. It says WPTO Software Demo Days here, but on your account, it might say your name - software demo days. I'll just click into there, and here you won't be able to see them yet, but as we distribute these items to you throughout the series, you'll see the whole series. This example was made for WECOP tool, so this is where all the WECOP tool folders are going to live, and interactive notebooks and stuff like that. The reason we use CoCalc is because of this feature. We have custom kernels that are created for each demo that we're using. So we have an OpenFAST environment set up for you guys today. Just kind of, decreases the barrier to entry on these demonstrations, which, as we all know, install can take some time. So hopefully we're skipping that step today. I'm going to pivot and actually log on to CoCalc with you guys, if that's helpful. Does everyone have the CoCalc URL? I can drop it in chat if not. Sorry, you might see yourself.
I just put it in there.
Oh, sweet. Thanks, Kelly. Awesome. So the sign-in button's right here, kind of in the center of the screen. You're going to sign in using that email you gave Kelly a while back. Okay. When you're in, you're going to do the same thing as the video. Go to your projects in the top left. And you're going to select your name - software demo days. For me, it's a little different, but I'm going to go into the project. And then we're going to navigate to the OpenFAST folder. And from here, you should be able to follow Hannah's demo. We're going to be using something similar to a Linux terminal on this platform. So yeah, assuming everyone's gotten here all right, I think I can just hand it back to Hannah, and if not, make a note in the chat or something, and we can try to help you out.
Yeah, and I just wanted to make a quick comment. I saw Elena's comment here, and I think it's relevant for everyone. I'll put this in the chat. If you have not already created a CoCalc account, please do and send it to me. We'll do our best in the background to add you to this class, but it does take some time to transfer the files and the configuration to run this. So it might not be done in time for Hannah's demo, but we'd be happy to add you to the CoCalc series, and then you'll be able to have the materials both from today and future courses. So, all right.
Sweet. All right. All yours, Hannah.
Great, thank you. Okay, I will reshare my CoCalc. Okay. So yeah, this is where it's really helpful to have feedback and interaction. Please, if you're stuck on something, just raise your hand or let me know. I'm really hoping that we can kind of go through this together and kind of have the, accomplish the intention of getting you somewhat familiar with running the software on your own. I will say, so I guess first, yeah, we'll navigate into the OpenFAST folder. And I think it's helpful to sort by type right here, just kind of make it a little bit cleaner for how we're going to look through these files within the folder. And we will be running OpenFAST through the terminal. And a big advantage of doing this on CoCalc, like Kelly and Megan and Dominic mentioned, they put a lot of work into getting this up and running on CoCalc. It's that in previous demonstrations that I've done, most of the time is taken up with just doing the installation and getting the attendees to the point where they can run the software on their computers. And we are skipping over that here, which is really great on one hand, because we can kind of go directly into showing you all the running of the software. But on the other side, that we don't go through the installation and getting it to where you can run the code on your computer if you want to in the future, which can be kind of tricky. So I have included in the files here this installing and running OpenFAST links. And so these are PDFs to be determined if it's going to load, but you can download these and look at them later on if you want to install and try to run OpenFAST on your own. So these give hopefully clear step-by-step instructions for the installation and the running, and there are also associated videos that are like screen captures of this same process with a voiceover posted on the NREL Learning YouTube. So if you want to, try and do that on your own, I would encourage you to take a look at these documents and those videos. I'll try to share a link to them after the tutorial. So that's it for doing the installation and running on your own if you so choose. So now I'm going to dive into the example cases that we have and how to start running some of them on this CoCalc platform. So if you sorted by type here, we have 4 folders on the top, which are variations of the MHK RM1 case. These are all on the OpenFAST RTest repository, so example cases that you can look at later. And they contain the necessary input files for the fixed RM1, the floating RM1, so again, the fixed bottom and the floating case. And then these AD underscore are versions of those simulations for running in Aerodyne only. So they're run with the Aerodyne driver, and they use just those, just the Aerodyne module to simulate the rotor hydrodynamics. Then we have another folder, PyDat-View, which is a visualization tool that I'm going to walk us through. There are a few different terminal files in here and X11 files, which allow us to run the terminal for the OpenFAST simulation and then a desktop environment for some of the visualization. And then also a document showing all the possible outputs from OpenFAST that's useful to have as a reference. So I'm going to just keep going. Please raise a hand if you're feeling really behind or need some extra questions as far as how to get to where we are. But I'm going to navigate into the MHK RM1 floating folder and just walk through some of these input files to kind of show you what they look like and what all needs to be there for an OpenFAST simulation. Again, this is starting with a full simulation using OpenFAST and all of these different modules for the floating case. And so there's quite a few input files here. But we want to start with this .fst file. So that's going to be the top level input file that is called when you run the simulation. So we'll take a look at that, open it up. And like I showed in the slides, these are text-based input files with this kind of value keyword description layout here. And if we just scroll through the top level FST file, you'll see different sections for inputs related to the simulation control, different features, environmental conditions, etc. So this section lets you choose the simulation time, the time step, the correction iterations, that sort of thing. So kind of set up how the solver is going to run. The feature switches and flags, this is where you turn off and on different modules. So you can say that I'm going to run the simulation with Elastodyne. You have a flag value of 1, Elastodyne, and then Beamdyne for the blades, a flag value of 2. There's a simplified Elastodyne, a flag value of 3, and then so on and so forth for the different modules. Inflow wind, Aerodyne, Servodyne, C-state, and you can switch on and off which modules are used here. And then there's also this MHK flag, which lets you specify if the turbine is not an MHK turbine, is a fixed MHK, or is a floating MHK. And so fixed in general, we mean it's bottom mounted, not using moorings, has the support structure below the rotor, floating, surface mounted or surface piercing or kind of mid-column, uses this the buoyant support structure and moorings, and has the rotor below the support structure. And this choice of 1 or 2 really needs to match up with the geometry that you're trying to model, since it has a big impact on those kind of definitions. The various environmental conditions, we have inputs for air density and water density separately. And then the other properties, so the kinematic viscosity, this is the kinematic viscosity of the working fluid. So if it's a marine turbine, that's going to be corresponding to water. Same thing for speed of sound in the working fluid, etc. And then this is where the input files that define the characteristics for each of the modules are specified. So if you said you want to model the turbine using Elastodyne, then you need to put in the name of an Elastodyne input file right here. And then Beamdyne, not used in this simulation, inflow wind, where that inflow wind file is located, Aerodyne, etc. Some output and linearization sections, and then visualization. So that's kind of the structure of the top level file. And then we'll go back to the folder where the rest of the files are stored. And I won't go through step by step for every single one of these, but just know that there is this kind of hierarchy of the .fst file is the top level that's called directly from the simulation. And then within that, you specify the location and the name of these module input files. For example, if we look at the Aerodyne, so this is kind of the primary input file for Aerodyne. So here we're defining all of our rotor air or hydrodynamic modeling options. The tower shadow, whether you turn that off or on, cavitation check and buoyancy for marine turbines, environmental conditions. You can specify additional conditions here to overwrite what's in the FST file, or just put default to use what's in the FST file. If you're using blade element momentum theory, options for that. The vortex model has its own input file that's specified here. And so this is kind of that second level input file, and then there's third level input files as well. So here, if you were using Olaf, you would specify the location of the input file for Olaf. Same thing for the airfoil polars. Those are specified here. The blade properties are a separate file, and you tell the code where to find those within that Aerodyne input file. So that's kind of how that works. The top level, second level, and then third level input files like the Aerodyne blade file. All right. I think next, we're going to go quickly back into the Aerodyne input file and then look at some of the outputs that we can specify for a simulation. So each of the module input files has this option to specify which outputs you want to be written out with the simulation. There's a very long list of outputs that you can use for OpenFAST. There's quite a few here that are specific to buoyancy, so a lot of buoyant force outputs in this specific simulation. And they're all, again, specified here at the bottom of the input file. And this, go back to OpenFAST for a minute. This outlist parameters Excel sheet is, again, on the GitHub repository, but it has the full list of possible outputs with descriptions and coordinate systems used for each module. I don't think we can look at the Excel file on CoCalc, but if you want to download it and take a look at it, that's a great reference for giving you an idea of the different outputs that are possible. All right, so we're going to start now trying to run this floating simulation. So we'll open up a terminal. I think maybe the easiest is to open up this term_commands if you have that one, or also you can do new here on the left and then Linux terminal. So either way, just open up a new terminal. And then there are a couple of commands that are kind of specific to this CoCalc installation and might not necessarily be the same as the way you would run this on your local machine. But for the purposes of this demonstration, we open up the terminal and then we activate Anaconda by running Anaconda 2023. And then we want to activate this OpenFAST environment that's been created. So now we should have our command line looking like this, OpenFAST environment, and then the command prompt. And so now, if you're familiar with some of the Linux commands, we can use ls to print out all the files in our current working folder. So we can see we are in the main OpenFAST folder, and we now want to navigate into this MHK RM1 floating. So we're going to do the cd command to change directory, and then MHK RM1 floating, and you can tab over for autocomplete. So that'll put us within the directory of the simulation that we want to run, and another ls to print out the files that are within that folder. And now we see we're in the same folder as the .fst file, and so we can go ahead and run the OpenFAST installation by just typing OpenFAST. Again, this might be slightly different for a local installation, depending on your operating system. But we type OpenFAST to execute the program, and then we provide the name of that top level input file that we're going to call. So OpenFAST, and then in quotes, mhk rm1 floating.fst, hit enter, and you should get some output that gives some information about the OpenFAST version that's being used, the type of turbine that's being modeled, and then it steps through as it runs the different modules, and then gives you some information on what's happening within the simulation. So in this case, it's initializing Mordyne, and then finishes that and says it's reading Elastodyne files, etc., and then gives you the time estimate. A couple minutes anyway to run this in at what we can get within that time. All right, so this again takes a little bit of time to run. So while that is happening, I wanted to go ahead and open up one of the visualization softwares that we're going to be using. So we can go back to Explorer, and then you can see here that this terminal file is still open. I'll go ahead and close some of these other files to kind of clean it up. But you can see this terminal file is still open and is calculating here. So we'll go back to Explorer, and then we're going to open up this PyDatView software. So this is a Python script developed by one of the OpenFAST developers to enable a GUI-based kind of quick visualization of the OpenFAST output. And so to run PyDatView, if you're running it on your local machine, you can do this through a terminal command, but because it uses a graphical interface for CoCalc, we have to use an X11 desktop. So we're going to click on this X11 desktop that we've already gotten, that's already been set up for us here in CoCalc. And then we should have in one of the windows a prompt, again, a terminal prompt, just like we had before. And then we're going to do the same thing where we're going to list the files. All right, we're in the OpenFAST folder. We're going to cd into the PyDatView folder. And then now we're inside this PyDatView folder, and the version that we're going to run, or the code that we're going to run is this pydatview.py. Yeah, question?
Yeah, how did you list the files in there? I
Yeah,
missed that part.
Is ls
Okay.
command. And so just whatever folder you're in, if you just type ls, it prints out the name of the files and folders that are within that specific folder.
Okay, great. Thank you.
Yeah. So now we can see, okay, we're in this PyDatView folder. The different files that are in there, the one that we want to run is pydatview.py. So we're going to run this with Python. So we type Python and then pydatview.py. Hopefully this opens up the graphical user interface that we can use to visualize the OpenFAST outputs. Oh, I forgot a step. We're getting an error here. But I ran into this yesterday, and I think The problem is we just need to activate Anaconda in this window and then run the Python command again, and it should work. Okay, so Anaconda 2023, and then run the Python command. And it's still giving an error.
Maybe try activating the environment again. I think that's
Oh,
where
the
the
OpenFAST
deadline
environment?
is. Yeah.
Oh, thank you. Yes. Okay. So again, somewhat different step on CoCalc than maybe on your local machine. But let's run Anaconda 2023. And then Conda activate OpenFAST environment. And then the Python command again. There we go. Okay. So if, like me, you had closed out of this frame, you could just hit the terminal, new frame, and then X11, and that will pop up this graphical part on the other side. All right. Is everyone generally to the step? We have PyDot running in the terminal on the X11 desktop, and then we have activated it such that the graphical part is showing on the right. There's not a whole lot to look at yet until we load in a file, but you should see this kind of file data tools bar, etc., on the right-hand side. Okay, I'm going to assume silence means yes. And so thumbs up. Yeah, Kelly?
Yeah, I just wanted to make a quick comment. I've been getting some emails about people having a hard time accessing their CoCalc account. And I just wanted to say that we've had a couple of instances where people created their CoCalc account with a GitHub account. And if you've done that, you'll actually need to go in and manually add the email address into your account to be able to accept the invitation to this series. So.
Thank you. Yeah. All right. So we were on this X11 desktop. We've got that activated. That took enough time that our simulation should have completed. We go back to the .term. And I believe the simulation has completed. It's not loading to the bottom of the terminal right now, but if we go back into the MHK RM1 floating folder, we can see that we have these output files. And so these files were not there before, they were generated during the simulation. So these .outs and .thumb files, we'll take a look at what both of them do. But for now, we're going to open up this MHK RM1 floating.out. So this is the primary output file where all of the specified outputs that you had in that, the Aerodyne, the Elastodyne, Hydrodyne input files up here, all of those outputs, again, that were specified at the bottom right here, are going to be, those values are going to be outputted every time step in this .out file. This .md.out is just specific to Moordyne, but we want to look at this file with all of the outputs. And then this .outb is a binary formatted output file. So containing the same information, but binary formatted. So we're going to just open this .out file to take a look at just the text version of the outputs. Not super meaningful in this version or in this format, but you can see this is just kind of what the raw output looks like. if you open this in like a normal text editor or something, you would see columns of the output name, and then the corresponding units, and then a column of that value at each time step. And so you most likely want to take this text-based output file and do something else with it, some sort of post-processing or visualization. And that's what we're going to do with this PyDAT view. So this is really, really useful for just like quick visualization of OpenFAST outputs. So here, back in the X11 desktop tab, we'll do File, Open File. And then we can see we're in the PyDAT view folder. We want to navigate out to the OpenFAST folder and then into MHK RM1 floating, and then down to select this MHK RM1 floating.out. So that output file we were looking at. And PyDAT view should work with either the text-based or the binary version. And then click open, and you can see now I will maximize the window on the right a little bit. But you can see that there is a list on the left of all of the outputs that are in that .out file. These are some of the buoyancy outputs that we had in Aerodyne, and then further outputs from Moordyne down below, as well as the associated units. And as you can see, if you click on each one, this just shows a plot of the time series of that output. So a really quick way to just visualize that text-based output file. Yeah, a question?
I fell off just for that last part. How did you navigate here in the X11 desktop?
Yeah, so do you have kind of the graphical interface showing without the file loaded in on the right-hand side?
Yes. I just
Okay.
have yes. I didn't follow the sequence of steps within it.
Sure, no problem. Yeah, so you go up to File in the top left of the GUI, and then Open File. And then we're in the PyDAT view folder, so we want to back out to the main OpenFAST folder, and then into MHK RM1 floating, which is a simulation that we just ran. And then we want to select this main output file, the .out or the .outb, and then hit open. And so for me, it just reloaded that same output file. But again, we can see time series of each of the outputs from all of the different modules. So just a really quick way to visualize what your simulation is doing. And then there's some different options down here of different ways to plot and visualize the data as well. So log plot, flip the axis, etc. All right. So that's run a simulation, visualize the output. And then I want to do a small modification to one of the input files and take a look at how that affects the output. So what we're going to do now is go into back into the MHK RM1 floating folder. So if you're a little bit lost, you can just click on Explorer on the left-hand side, and then into this input folder here, MHK RM1 floating. And then we want to change some of the inputs and rerun the simulation to take a look at the effect on the output parameters that we've specified. But first, because this .out file is regenerated every time, we're going to click on it and then rename just so we preserve this .out file so we can do a comparison between the first simulation and the second. So MHK RM1 floating, and we're going to name this run 1, rename. Okay. So we've renamed this as run1.out, so it's not overwritten. And then we want to go into now the inflow wind input file. Take a look at that. So here we've specified that the wind type is 1, meaning steady. So like I said, we're modeling this case with a steady wind speed with a shear exponent. This is actually 2.9. I had intended this to be 1.9 and then increase it 2.9 for the test case. But since we already ran at 2.9, let's go ahead and bump it down to 1.9 and run at that speed, which is actually the rated speed of the turbine. So we just bump this down to 1.9 and then save. And then go back over to Explorer again. And so we've modified this inflow wind file, and then we're going to rerun the simulation and take a look at the new output file that's generated. So we go back to our terminal. Yeah, Rob?
Just to quickly clarify that inflow wind speed, that's the water current, not wind on the surface platform.
Yeah. The H wind speed is, yeah, just the horizontal wind speed. So the X direction wind speed. And it is the wind speed at whatever reference height you specify. So usually hub height. And then you also specify the shear exponent that's used in the power law. So OpenFAST, when you use this steady wind case, uses a power law representation and just takes, yeah, the 1.9 or whatever reference wind speed and then creates a profile over the full height of the vertical distance that you're modeling using this shear.
So this is the water velocity that's driving the turbine, not wind speed at the surface?
It's the water velocity that's driving the turbine at the reference height. Sorry, your audio is a little bit choppy. I'm not getting everything.
All right, try to get closer. So then when you're setting like power law, so it knows that this is a surface mounted turbine and that I guess how would it, does it know that the surface is at a certain height? Like we're not, it's not like off the seabed, right? This is off the surface.
Oh yeah, good question. So for marine turbines, this is a little bit tricky. So we are trying not to confuse the coordinate system definitions in inflow wind as much as possible. So the reference is the seabed in this case for a marine turbine. The reference in inflow wind is the seabed. So you define this as 24.8 meters above the seabed is what we're going to say the hub height is. But in, for example, our Elastodyne file, that's going to be defined as negative. So the inputs are defined in Elastodyne and everywhere else as negative, so relative to the mean sea level, except in inflow wind. And then there's some internal adjustment that takes all of that into account. And when, say, a point on the blade needs to know its velocity, it queries inflow wind. There's some adjustment that happens to tell inflow wind to look at not negative 24, but actually, you know, positive whatever compared to the seabed as the reference in inflow wind. So from the user perspective, that's kind of the only distinction that you need to know, and that is included. That's written up in the documentation as far as like what reference point you use for each of these definitions. But inflow wind is the exception, and that's just because we are trying not to have to deal with lots of negatives in the shear definitions and all the other definitions of the profiles. So that's just adjusted later on. All right, so it's taking this, again, this inflow speed, and then let's go back to our input folder here. And then, like I said, we're going to rerun and generate a new output file at this now lower 1.9 meter per second. So we'll go back to the terminal. And then, okay, all I had to do was hit a button and the bottom of the terminal popped up. So it does say from the previous simulation, OpenFAST terminated normally. So that means the simulation completed. So we can just arrow up to rerun this command. So now running the same simulation, just slightly slower inflow speed. So arrow up, hit enter, and it will run and regenerate these files. The inflow current, okay, yeah, question from James. Yeah, so the naming is a good question. There are a lot of places where it's referred to as wind, and it's assumed that for marine turbines, it's the same. It's just the current, and that was really to avoid doing a lot of internal and external renaming of variables that would potentially mess up workflows for people who had kind of automated inputs and outputs that they had generated on their own for setting up OpenFAST simulations. The MHK flag, if you set that to 1 or 2, then inside the code, it uses the water density as the working fluid. So it uses the properties of water as the working fluid. So if we go back and look at that FST file, then an MHK flag of 0 is going to pull the air density for the working fluid, and MHK flag of 1 or 2 is going to pull the water density. And then it's assumed that you give the corresponding values, kinematic viscosity, speed of sound, and all that for the working fluid that you're choosing. Does that make sense?
Yeah. So if it's not an MHK turbine, it's a wind turbine.
Exactly.
Cool. Okay. Thanks.
Yeah. Yep. The actual wind on the surface platform is not modeled. That's a good question, Rob. Cool. Yeah, and James. But yeah, so in this case, if you do have wind and it's loading the surface piercing part of the platform, it's not something that's modeled currently. That's something that we would like to have in the model in the future, and could potentially be more important for marine turbines than for large offshore wind turbines where it's currently neglected. But yeah, we don't have that speed in there because it's not something that we capture in the model.
Great, all right. Thanks.
Yep. Okay, so now going back to our terminal file, it looks like the simulation has completed. And so we can go back into the MHK RM1 floating. And now we have a dot out and then this old run 1 dot out. I'm going to go ahead and rename the second one as run 2, just to keep it straight for ourselves. And then we want to go back to the PyDAT view visualization. So right now we have the previous file, the run 1 file loaded in here. And I want to kind of demonstrate that we can run both or load 2 files in here at once. It looks like this is a little bit frozen, so we might have to reload it. If yours is frozen like mine is, then you can just Control Z to kill the terminal command, and then we can try opening it back up. Let's see. Still frozen. Let's try to close the frame. Run again. And then add a new X11 frame. Oh, okay. Might have to fully end the X11. Or Megan, if you have any thoughts here, please feel free to jump in.
Yeah, maybe just closing out.
Yeah, I think I just need to reload the X11. Okay. So back to the OpenFAST folder.
Oh, there they all are.
No, there are many. Here we go. All right. This looks like one that's active. So raise your hand if you if that didn't work out for you and you're still experiencing frozen or not able to access an active PyDAV view window. I think this is just a coke-out thing. This doesn't usually happen when using PyDAV view locally. But we're going to go back into the MHK RM1 floating, and then we're just going to add run 1 for now. So open up run 1, so the previous simulation. And then I just want to demonstrate how you would add an additional file on there. So you may have to resize to see, but up here in the top right of the PyDAV view, there should be a little plus add button. And you can click on that and then go back through and now select the run 2. We'll hit open. And now we have both of those files loaded in. So we can switch back and forth between either one, or you can shift click and multi-select. So you can compare directly the outputs from one simulation to the other. So again, you can see here the first run at a different inflow speed than the second one. That's affecting the platform surge. I won't read too much into the actual values here, again, because this isn't a converged solution. It's just the first few seconds, but you can see already the impact that just changing that inflow velocity has made on the initial platform motions. So again, that's really convenient to be able to do kind of multi comparison of the different outputs in the same view.
How did you get them both on the same graph?
Yeah, so you should, in your PyDAV view, can you see this add button in the top right here?
Yes, I have them both added. I can see them on the left side, but they're not displaying.
Oh, I see. So you just click and then shift click. And so, yeah, that is multi-select for all of the files that you have loaded. All right, any other questions on the PyDAV view and visualization? One more file type I want to point out is the .sum file. So we can navigate into the, again, the MHK RM1 floating. And then there's several .sum files for the aerodyne, elastodyne, hydrodyne, etc. Let's click into the aerodyne sum file. And this can be, these files can be really convenient for debugging. So they basically just give you a summary of the inputs that were used by the simulation. So kind of showing you what the simulation took as the input from your specification. So a summary of the options that were selected from the aerodyne file for the general options, blade element, momentum theory options, and then a summary of the output channels that were selected, and then buoyancy parameters are printed out here. So the hub and nacelle volume, and then the total blade and tower volume that was used by the code. These are specified element-wise in the inputs. So it's helpful to show what the code is interpreting as the total volume of those components, and then summary of the blade definitions. So the inputs that were in the blade input file. So again, those can be printed out optionally, turned on and off for each different module, but can be really helpful for debugging and providing some additional information about kind of what the code interpreted as your inputs. Okay. The kind of last part of the demonstration that I wanted to do involved another visualization tool. So OpenFAST can output VTK files, which can be visualized in ParaView. And when we tried running this previously on CoCalc, ParaView was just kind of so computationally intensive that it took a really long time to actually load and visualize. So I think for this part, I will just run that locally and kind of show you what it looks like. But the steps are generally the same, or should be the same, as if you were doing it on CoCalc yourself. So what I'm going to do at the moment is actually stop sharing for a minute, and then set up the local simulation for you to follow along. Yeah, like Kelly said, you can definitely try to still follow along on CoCalc. It just might be pretty slow, and I didn't want to take the risk of it not working.
Yeah, I just wanted to say for the students, if you wanted to follow along, it's something you could do, after the fact, but it is there available to you.
Okay. Yeah. So I'm just going to share my desktop now. And I'm here in a terminal on my local machine, and I've navigated to the folder where the files that I'm going to be working with are stored. So just where these, the OpenFAST input files are stored. So here you can see now I am in a folder that's going to run just the aerodyne driver. And I have these two same folders here, the AD, MHK, ARM1 fixed and floating. And so if we look in the file explorer, we'll look at this MHK RM1 fixed case. So these should be the same or similar files as what is on CoCalc. And you can see instead of a .fsp, we now have a .dbr. So this is the top level code that's run just by the aerodyne driver. So again, that's running aerodyne by itself, uncoupled from the rest of the OpenFAST modules. So I just wanted to show an example of doing that for aerodyne and some of the visualization that you can do. So I'll open up this Aerodyne driver file. And you can see now we have some kind of similar inputs as the .fst file that are needed for the simulation to run. So again, the time step, the total time, the environmental conditions, we don't have the FFT file, so those are specified here now. The inflow data, and then the turbine geometry and motion. So you can prescribe rigid body motion, and that can be modeled with the driver by itself. And then down at the bottom, we have these output settings. So this line here, the right VTK, you can choose to output or not output these VTK files. So we're going to choose one to write the files, and then we're going to choose surfaces as the output type rather than lines. And then you do have to say, because OpenFAST doesn't inherently know information about the size or the shape of the hub and nacelle, you do just specify that here just kind of for visualization purposes as far as how big the hub and the nacelle are, just so the turbine looks correct in the visualization. So now that we have these with these options selected, on my local installation, the command is a little bit different with the .flash, but you should be able to run this on CoCalc with just the command Aerodyne driver, just the same in the terminal as we are doing with the OpenFAST, and then specify the location of the top level folder or file. So in this case, we are outside of the AD fixed folder, which is what we're going to run. So I'm just going to say that Aerodyne driver file that we want to call is within this MHK ARM1 fixed folder, and then it's named AD_driver.dvr. So again, the command to call the Aerodyne driver and then just telling it where that top level input file is runs very quickly. It's just the one module by itself, so it's a lot faster than the full OpenFAST simulation. And then we can go back to our folder here where we now have a .outb, so the output file for the Aerodyne driver. And then we have this VTK folder and some files inside of that. And this is what we're going to visualize with ParaView. So I'm going to open up ParaView on my desktop. It's a little different. If you're doing it in CoCalc, you can do it through the X11 application, just like we did for the PyDat view, but just type ParaView in the command instead of the Python PyDat view. And then it opens up this ParaView application. And then I'm going to open files, navigate to the location, which always seems cumbersome for some reason. And then we're inside this AD fixed case. We'll shift, select all of the files, hit OK to load them in, and then apply. And then we can adjust the viewing here in ParaView to see the outputs. So we can hit this button with the 4 arrows pointing out to adjust to the screen size. And then the navigation, as far as like turning the view, is probably different on your device, kind of depending on if you have a Mac or Windows device or how your mouse commands are set up. But you can control shift click to kind of experiment with changing the view. And so you can also use these kind of standard views to just get a side or top or front view of the turbine. And then we can do this magnifying glass zoom to kind of zoom in. And so what we're looking at here is this fixed turbine case. And so this kind of flat top part here is the what's defined as the ground surface. In this case, it's the water-free surface. So you can toggle each file off and on to kind of show what corresponds to what, the different blades, the base surface, the hub, the nacelle, etc. But I think it's really helpful to be able to look at the location of the turbine relative to what is defined as the ground surface. So in this case, the sea surface. So again, this is the fixed turbine, and so we're expecting to see the free surface up above with the tower and the base below. And then we'll run the same thing for the floating. And I want to show you what that kind of layout looks like in comparison. All right, any questions on that so far? Yeah, Rudy.
Can OpenFAST model fully submerged platforms that are not piercing the surface for MHK?
Yeah. Yeah,
Okay.
it can be either surface piercing or not. You just kind of specify that location. Yeah. So we're now going to rerun, but for the floating case instead of the fixed. So now we're running this Aerodyne driver floating case. So we're specifying that it's in the floating folder, but the same top level file name, kind of just the common naming convention. And you can see here now the creation of these .thumb, .out, and VTK files. So now we have the VTK files for the floating case. We can go in and shift, select, and delete, hopefully all of them at once. So clear out the fixed case files and then go in and open up the floating case files. Apply. And then we'll adjust our view here, and you can see that we now have the turbine base as being defined up here at the sea surface, and then the tower, nacelle, hub, etc., coming down from that. There's a gap here just because this is where the platform would be. And then the platform's not modeled in Aerodyne. So we're just modeling this part that is kind of the tower and then the rotor. And so that model in Aerodyne starts a little bit below the sea surface. But again, we can prescribe motion of this part of the turbine that would be seen as if it was connected to a platform, and you can see what the rotor performance hydrodynamics are for that prescribed motion. All right. Any questions on that? Yeah, apologies that that wasn't working, didn't seem to be working super well on CoCalc. But hopefully this gives you an idea of the kind of visualization tools that you can use and the just the high level method for running OpenFAST simulations, the files that are required, the ways that you can change the inputs, that sort of thing. We've got about 10 minutes left. If there are any last questions or asks for demonstrations of a particular case, I'm happy to take that.
I'm just doing a CoCalc survey in the chat, so please note.
while everyone's doing the
Nice.
survey, I can start sharing the screen again and wrap us up here. Thank you so much, Hannah, for the presentation. I think it was a huge success. It was so good to see everyone engaging with CoCalc and doing demonstrations. So it's a really big win.
Yeah, thanks so much for setting that all up. I think we definitely got to do some more demonstration than we would if we were trying to do the installations ourselves.
Okay, here we go. So to wrap up, the next CoCalc, the next, sorry, CoCalc's on the mind. The next demo day will be on Wednesday, May 7th, and will be for Moordine. And so be sure to tune back in. Again, that will be using CoCalc just like this one. And so next screen. So as we've been talking about the CoCalc platform, if you weren't able to join using that interactive platform today, there's some instructions. These slides will be shared in order to get your account set up and then send that email to Kelly at that email address so that we can get you set up for the next demo. And then again, just some logistics to wrap up. The day of checklist is just having internet connection and having that that CoCalc thing set up so that we can help you get in there. And just I guess there was questions all throughout about the actual substance, OpenFAST. Are there any other questions we can answer about software demo days broadly? I guess just opening the floor for that. If there aren't, we can just give another round of applause for OpenFAST or talk about more discussion questions.
Can I ask a quick question? Are there any other questions for Hannah?
I was going to ask if you could speak to the availability of the recordings for these.
Yeah, so we, unfortunately, this is a Sandia Teams meeting, so people who are external participants will not have immediate access to this, but we are downloading them, and then we'll share the link to the recording that'll be on Google Drive for students to have access to. And eventually we are planning to release them publicly, but right now we don't have the authorization to do that.
I guess I can stop sharing screen.
I have an OpenFAST question. Can OpenFAST be coupled to other external codes or used in other ways?
Yeah, so there were a couple options that I mentioned throughout the presentation, like being able to couple to Orcaflex, the commercial code, use some inputs from like turbulence files from like the Bladed and Hawk2 softwares, and then also being integrated into the larger like control co-design software CTOpt that we've developed. There are some more interfaces and options that I didn't fully mention. There's a LabVIEW, or excuse me, MATLAB interface to run OpenFAST through MATLAB, and some connections that are being built right now with other codes. I think there's some OpenFAST connection, as I mentioned, to the Sandia code ONs, and I think also to Project Chrono is the connection that's being developed right now. So there's a lot of flexibility and ability to kind of call pieces of OpenFAST from other codes or have it call other codes. And we're also working to develop additional C bindings, which allow passing of information in and out of one module in kind of a generic way to make those couplings easier. So that's something that there's a lot of capability for that, and we're expanding it as well.
Awesome. Yeah, thank you.
Yeah, thanks. Right.
Question for me. What's the accuracy of the OpenFAST system?
Yeah, that's a little bit of a loaded question, I think, like with all models or all modeling tools. And, obviously a lot of it depends on like the input that you give the model to begin with. But there's been a lot of verification and validation work done on the wind side with OpenFAST. Not something that we've done a lot of for marine turbines yet, but under the Aquarius project that I mentioned, we have a couple of collaborators at Sandia who are working on that project with us, and they are leading the V&V efforts. So to really do kind of a rigorous systematic evaluation of OpenFAST accuracy compared to experimental data for including all these new features that we've added in specific to marine turbines. So yeah, I think that'll be really helpful in kind of like illustrating how all the modeling tools are working and what where we can apply them well. Rob.
Hi, Hannah. Question on that task. So are there opportunities for others to be involved in that? So, for example, workflow on my projects involves the use of Proteus DS to do a lot of the same things that this code's doing, and I'd be curious how our workflow and output compares to OpenFAST and all the components.
Yeah, we have been working with a developer actually who was trying to do a similar modeling in Proteus and ended up switching to OpenFAST because they weren't able to get a good enough turbine model in Proteus. And so I think, yeah, that's something that I would be curious to hear about as far as like what your workflow looks like and specifically what you're trying to model and how that kind of overlaps with what we can do in OpenFAST. And I think as with, kind of within the code development project, we have some, maybe a good teamer project for sure. We also have a task to kind of look at what we think the direction of the code should be moving forward. So in the future, kind of what do we want turbine modeling to look like? And that kind of involves looking at the different currently available options. And so I think that's something that could be useful for that task as well. But yeah, this is the second time I've heard someone say that there's kind of some modeling similar cases in Proteus and OpenFAST. So I'd be curious to hear the comparisons.
Great. That's certainly exciting future works there. And thank you so much, everyone. I think we're getting right at time here. So if there's no other questions, just thank Hannah again, and thank you all for your participation and coming to this demo day, and invite you to come to the next one on the 7th. So thanks, everyone.
All right. Thank you, everyone. I appreciate your questions and engagement.
Thank you so much, Hannah. Great presentation, and looking forward to seeing everyone at the next demo day. Thank you so much.